Assalamualaikum warahmatullahi ta'ala wabarakatuh and good morning. I'm Dr. Sababau from the Physics Section Pusat Pengajian Pendidikan Jarak Jauh Universiti Sains Malaysia. This is course JIF 318 Quantum Mechanics. We are in chapter 3 on Schrodinger equation. This segment, unit 3.8, is on the time-independent Schrodinger equation, or TISE, TISE. The objective of this segment is to describe the effects of time independence on the Schrodinger equation. Consider a special class of potential where V is a function of R only. That means of radius. We can consider this as in a spherical potential, such as in an atom where the potential is due to positively charged nucleus and the field is going out or going in 3D, 3 dimension. Consider this special class of potential. V is a function of R only and is independent of time t. Example, the potential and electron fields in an atom. So an electron field a potential based on this, where V is a function of R and is independent of time t. That means the potential or the force experienced by an orbital electron is constant with respect to time. So it is independent of time. So we start with the Schrodinger equation. Okay. Now V is only a function of R. And on the right hand side, the operator of E is IH bar delta per delta T. And this operator can be replaced by E, where E is the energy. Okay. Using superposition of variable, assuming a solution of the form capital psi equal to small psi in terms of R and chi in terms of T. We have two variables, R and T. Even though we say that V is the potential V is only independent of R. Okay, but the others are still based on R and T. Then we substitute the capital R with substitute the capital psi with psi and chi. So here we multiply with chi and psi, chi and psi, chi and psi. Chi in terms of T cancels because it is available in all the three terms. So what is left is just the terms of chi. And the terms of small psi, but psi is dependent only on R. So now we have this solution or the equation where it is, or the Schrodinger equation depends on R only and there is no terms in T. That means independent of T. So this is the Schrodinger equation, the derived Schrodinger equation, which depend on R and is independent of time t. Okay, so since psi r is available on both the term in the left-hand side, we can bring it out and we can factorize. Okay, psi. What is left inside the square bracket is negative h bar squared per 2m del or nabla squared plus v. Okay, this is basically the same form of the eigenvalue and eigen function form. H, let the term in the square bracket be h and multiply by eigen function psi equal to energy is the eigenvalue multiplied by the eigen function psi. So where h is equal to negative h bar per 2m nabla squared plus v. This is a new operator. Okay, remember that when we have this form, this is the coefficient of psi on the left hand side must be an operator. So H is an operator. It's a new operator called Hamiltonian, and this is only for time independent Schrodinger equation. So Hamiltonian exists only for time independent Schrodinger equation. So this Hamiltonian is derived from the separation of variable we have done above. Okay. So now the form is still there, the form of eigenfunction, eigenvalues, and operator. And this new operator is basically Hamiltonian, defined as negative h bar squared per 2m nabla squared plus v. So basically the solution for time variable definite energy, that means now when we say that time independent Schrodinger equation, most of the time we will concentrate on the energy. Okay, so consider the requirement that the wave function capital psi be an eigenfunction so that it corresponds to a state of definite energy E. Basically, we are looking at the right hand side of the time independent Schrodinger equation in the previous slide. Okay, IH bar delta per delta t is actually the operator for energy E. Again, you can see that this is the same form as the rule for the eigenvalue and the eigenfunction. Okay. On the left hand side, it is the operator multiplied by the wave function. On the right hand side, it is the eigenvalue multiplied by the wave function or eigenfunction. Okay. Since we have this differential of delta t, so when we replace capital psi with psi multiplied by chi, so the differential is for chi, because chi is in term of t, while small psi is in term of r, so it's will not be differentiated. Okay, so you multiply both sides with psi chi, small psi and chi. Okay, but the psi cancel because it existed on both sides. Psi cancel, chi cannot cancel because one of the chi on the left hand side is now being differentiated. So we have this different differential equation. Okay, and finally we have this solution for chi in terms of time. Okay, I would like you to try this, how to get from the differential equation into the solution of chi. So the full wave function capital psi is equal to small psi multiplied by the solution for chi, which is exponent negative I et per h bar. Okay. Often many physical quantities can be derived from time independent wave function small psi alone. Yeah? Many physical quantities, especially in atoms, because the structure of atom mostly are stable, time independent, and the potential depends on R only. So basically, here we find that most of the physical quantities depend on R only and independent of time. Example, probability density for the particle. Okay, probability density is defined as the capital psi conjugate multiplied by capital psi. Okay, when you have capital psi, you have two variable R and T. But when you put in the value, okay, the value here, the value of the full wave function, then the exponent basically cancel each other. What is left is just small psi r conjugate multiplied by psi r conjugate. I think I'm wrong here. This should be r at the top here. It should be psi r alone. That means depends on radius only. So basically, if you want to determine the probability density, it can be in the form of the full wave function, capital psi, or you can just use the small psi representing the probability density with respect to r only. Okay. So basically, it is applicable. That means the equivalence of the full wave function and the wave function depending on r only can be used in many other situations. For example, if you want to find the expectation value of any observable. When we say observable, it can be position, can be momentum, can be energy. Okay, so we represent it with small o here. So this is the expectation value of O. You have the integration sign here. Then full wave function conjugate, capital psi with a star there. Then in between the conjugate and the wave function, you have the operator for the observable. If it is position, it's just x. If it is momentum, then you have the differential there, also with energy. Okay, so when we put in the value of full wave function as small psi and chi basically is just exponent. So this one will cancel each other, the two exponent, because one is the original exponent and the other one is conjugate. So we are left with this. Basically, you can replace the capital psi with just the small psi, which is dependent only on r. Okay, so the expectation value can be in the full wave function capital psi or the wave function small psi, which depends on r only. This is for time independent Schrodinger equation. So both the probability density and the expectation values are independent of time. From the expression involving small psi, there is no time variable there. So it is only depends on the r. Apply only to states of definite energy which satisfy the time independent Schrodinger equation. And these states of definite energy is called stationary state, or maybe in anatomy you can say as energy levels or something like that. Okay. So as a conclusion, Hamiltonian operator is defined for time independent Schrodinger equation only. Probability density and expectation value are independent of time. It depends on r only. Apply to a definite energy state called stationary state. Thank you very much for your attention.